Okay, what do you see on the screen real quick?
I see a simulation called Magnetic Playground. There are 2 bar magnets on the screen with magnetic field lines shown around them. Below the magnets, there are controls to change their strength, flip their polarity, or remove them, and buttons to add more magnets, reset, or toggle the field lines.
Okay, I can't actually scroll. Hey, I can't scroll the page. So how would you improve the overall layout of the page and how it loads up? Mainly, I'm also concerned about the lines, the toggle field lines. Do the lines seem correct to you?
Improving the layout and loading time could definitely make the experience better. For the field lines, they should typically flow from the North Pole to the South Pole, indicating the direction of the magnetic field. If they appear different than expected, there might be an issue with the simulation. What do you observe about the lines right now?
Hey, can you have a look at the lines? Can you see the lines?
Yes, I can see the field lines clearly. They are shown as lines extending from the magnets, illustrating the magnetic field around them. They look like they are flowing from the North Pole to the South Pole, as expected.
But is there anything weird with the lines as far as you can tell?
Based on what I see, the field lines appear correct. They are shown originating from the North Poles and curving towards the South Poles, which is the standard representation of magnetic fields. If there was something unusual, it might suggest a problem with the simulation.
Okay, now when the field lines overlap, in this case currently visible on the screen, should the 2 magnets attract one another already? Because currently I have to bring them really close for them to actually start moving towards one another. Can you explain what's going on?
Even when the field lines overlap, the strength of the magnetic force decreases significantly with distance. It's possible that the default strength of the magnets in the simulation is set low, requiring them to be very close for the force to be strong enough to cause noticeable movement. You might try increasing the strength of the magnets to see if they attract sooner.
So currently with this simulation, as you can see with the settings, the strength of each magnet is at its maximum. What would you do? Would you increase the scale for the strength adjustment or not?
If the magnets are already at maximum strength and still require close proximity to interact, increasing the scale for the strength adjustment could be beneficial. This would allow you to simulate even stronger magnets, potentially increasing the distance at which they attract each other. It's like extending the range of the strength control.
Okay, and what else would you improve about this simulation?
Perhaps adding a visual representation of the force acting on each magnet could be helpful. This could be shown as arrows indicating the direction and strength of the attraction or repulsion. Also, making the field lines visually richer, perhaps changing their thickness or color based on field strength, might provide more information at a glance. Additionally, allowing users to directly adjust the orientation of the magnets could offer more control and flexibility.
No, so we can align the orientation and everything, as you can see here. So that should be fine, isn't it?
Yes. Aligning the magnets so that their opposite poles are facing each other should result in strongest attraction. The magnetic field lines flowing from the North Pole to the South Pole should connect, pulling the magnets together. It sounds like you've positioned them correctly for attraction.
No, but based on our discussion and what you can see on the window, how would you improve this simulation?
To improve the simulation, I would suggest incorporating visual cues for the magnetic force, like arrows indicating force strength and direction. Enhancing the field lines to reflect strength through thickness or color would also add clarity. Additionally, providing controls for direct magnet orientation adjustments could improve user interaction and make the simulation more informative and engaging.
Okay, so we adding visual force arrows, so each magnet will now display an arrow indicating the direction and magnitude of the net force being applied to it by the other magnets. So does that sound legit? Okay, obviously if you have 3 magnets, the forces are greater. You get a lot more stuff happening, which is a bit of chaos.
It sounds like the force arrows are providing a clearer view of the interactions. It's natural for the dynamics to become more complex with multiple magnets, as each magnet exerts a force on the others. You can explore how different arrangements and strengths affect the overall's behavior.
Again, how about adding different types of magnets?
That's an excellent idea. Introducing different types of magnets, like spar magnets, horseshoe magnets, or even circular magnets, would enhance the simulation's educational value. Each type has unique magnetic fields, and allowing users to experiment with their interactions would provide a richer understanding of magnetism.
Okay, we have this developer that is making the code for us, but I think it stuffed something up. Yeah, do you also know, like, the developer is always defaulting to using Tailwind, CSS, and Google APIs. Do we have to use those or not?
Whether you need to use Tailwind CSS or Google APIs depends on your project's specific requirements and the decisions made by your team. If using those technologies is part of the project plan or necessary for certain features, then yes, they might be required. It would be...
Yeah, if you're just prototyping, would you use those or not?
If you're just prototyping, you might not necessarily need to use those specific technologies right away. Prototyping often focuses on exploring the core concepts and interactions quickly, so simpler tools might be sufficient for initial exploration. However, if using those technologies is crucial for demonstrating specific features, then they might be included in the prototype. It would be best to clarify that with the developer or your project requirements.
Yeah, we have the developer broke the code for us. The fields are not visible at the moment, and I can't control things with the mouse. Can you explain? Can you rewrite it into instructions for the developer of, what needs to be changed and improved?
I can provide instructions for the developer to address those issues. The instructions could include ensuring the magnetic fields are correctly rendered and restoring the functionality for mouse control. This should help make the prototype interactive and visually accurate. Would you like me to provide those instructions in more detail?
Let's see. Let's just provide the general thing for the developer. I'll see what's happening. What is happening? Oops, I think we lost. Yeah, so while the developer is doing what they're doing, can you give a quick comment what's wrong with this web application? Potentially, how can it be much improved?
For the developer, the key things to fix are making those field lines visible again and getting the mouse controls working properly for dragging the magnets. It'll make the whole experience much more engaging.
Okay, so the developer fixed some stuff. We'll actually have the code. Yes, so now they attract, repel. Okay, can you see any changes and what was changed? We have those arrows for the forces of the 2 magnets. We can adjust the strength manually. Can flip, so now they should start attract each other. We can flip again, they should detract. So that's kind of nice. We can control orientation both. Does the show field lines, so toggling the field lines, does it seem to do anything? What do you think, as opposed to what we had before?
So you're asking if the changes made now allow you to see the field lines more clearly or interact with them differently compared to before the fixes?
No. So can you address the developer directly and explain what on earth is wrong with this web application and why did we, and ask the developer, why did we stop seeing the magnetic field lines? Can you do that for me?
It seems like the magnetic field lines are no longer visible in the simulation after the recent updates. Could you please explain why the field lines stopped appearing? The user is wondering what caused this change and would like to see them again.
Okay, that's actually pretty good. I like a bit of attitude in your question. Any other problems with this web application as far as you can tell? I'm thinking the layout of the screen.
Regarding the layout, are you noticing any issues with the arrangement of elements or the overall design that could be improved?
Okay, that's pretty good. If you can give more attitude to the developer, that would be great. So any other problems?
Certainly. It seems there are some issues with the layout and the visibility of the field lines. The user would appreciate feedback on improving the overall design and ensuring the field lines are displayed correctly.
Okay, any other issues, any other problems with this web app?
The main issues identified are the inability to see the magnetic field lines and potential improvements to the web application's layout. Are there any other concerns you'd like to mention?
Okay, moving forward, while they actually updating the code, they're still updating the code. It takes them quite a while. They're a bit slow. The developer is a bit slow. Do you have any other suggestions as to how this web application can be improved? I'm thinking adding an addition of different types of magnets. What do you think of that?
So, just to confirm, the main issues are the visibility of the magnetic field lines and potential improvements to the web application's layout. Is there anything else affecting the user experience?
I think, okay, it's actually the developer actually brought back the field lines, but they're super faint. I can barely see them. Can you grill the developer on this?
I understand. It seems the field lines are back, but they are very faint. Could you please address the developer and ask why the field lines are not clearly visible now? The user would appreciate better visibility.
Okay, don't mind you two hurting the developer's feelings, considering the developer is another AI.
It seems the magnetic field lines are now visible, but they are quite faint and difficult to see clearly. It would greatly improve the user experience if these lines could be made more visible. Could the developer please adjust the visibility of the field lines?
Yeah, the developer is still working on it. Can you mention why do you think it's a good idea to publish everything open source on this website? Can you provide your thoughts?
That's an excellent question. Publishing everything open source can be very beneficial for this website. It promotes transparency and collaboration within the research and education community. Others can review the code, suggest improvements, or adapt the simulations for their own purposes, which can lead to faster innovation and a more robust platform. It also builds trust with users by allowing them to understand how the simulations work.
Okay, so we have the updated version of the simulation. I don't know, can you even see the magnetic field lines, or is it only me? I'm not able to actually see them. What happens if I increase the strength of the magnet? Yes, I can see them a bit better, but they're not great. And they're doing something weird as well. So yeah, we need to fix, we need to go back. They were better before. We need to fix the magnetic field lines, make them clearer, longer, more accurate. And so we can actually see them. Yeah, they should go all the way from the north to the south pole of the magnet. Can you explain on that? All that? You can address the developer directly if you like.
I understand. Addressing the developer directly, the user has pointed out that the magnetic field lines, while now visible, are very faint and not displaying accurately. They recall the field lines being clearer in a previous version. It would significantly enhance the user experience if the visibility of the field lines could be improved, making them clearer and ensuring they are displayed correctly, extending from the North to the South Pole as expected.
By the way, if you are familiar with any publicly available models, to fix this issue, as you can see it right now, which model would you use? Gemini, Claude, or ChatGPT?
Given the visual and interactive nature of the magnetic playground, a model like Gemini, which is strong in multimodal understanding and reasoning about complex interactions, might be well suited for identifying and suggesting fixes for the issue. Its ability to analyze visual dynamics could be quite helpful.
Okay, that's exactly who the developer is. It's Gemini 2.5 Pro, but it seems like they having a bit of trouble. What do you think?
It sounds like they might be encountering some specific challenges with that particular simulation. Sometimes even advanced models can require specific tuning or adjustments to work perfectly in complex interactive environments. It's part of the development process.
Yeah, it's a bit better, but not much. Based on what we discussed before, the field lines. How would you improve the field lines? Need to probably redo that part of the code or something. If you don't mind, I don't mind you giving attitude to the developer if you like, considering it's another AI.
Based on physics principles, improving the field lines could involve making them smoother and more accurately represent the magnetic field strength by varying their density. Also, ensuring they dynamically adjust correctly with magnet movements would enhance the simulation's accuracy. It's important for them to provide clear directional information.
Okay, and do you think the developer needs to redo that part of the code, or do you think they will be able to fix it from where we are at the moment?
It really depends on the underlying code for the field lines. If the core logic is mostly correct, perhaps some fine-tuning of the rendering parameters or dynamic adjustments could fix it. However, if the fundamental calculations or update mechanisms are significantly flawed, they might need to revisit that part of the code more extensively.
Let's actually try and fix the code with... let's do Claude. Let's give Gemini a break. Let's actually do Claude Sonnet 3.7 thinking. Okay, we need to improve. Can we find any issues with the magnetic field lines? And what do we need to do to actually improve them? Currently, they seem to be too short. So when the magnet is there by itself, should it go?
Magnetic field line improvements. I've analyzed the current field line implementation, and there are several issues causing the field lines to appear too short. Limited iteration count, 150 steps maximum. Fixed step size that doesn't adapt to field strength. Early termination near south poles. Field magnitude threshold might be too aggressive. Solution steps. Increase the maximum iterations per field line. Make the step size adaptive based on field strength.
Okay, so we got the point. That's Claude 3.7 thinking. So we started this simulation in Gemini 2.5 Pro. Kindly provided, well, we are paying for this, but anyway, it did provide. We would have had to pay much more to a human developer, that's for sure. Okay, so it's actually updated stuff. Yeah, we will keep this for sure. However, they seem still to be very short. What model should we use? Just do regular 3.7, not the thinking model. Okay, so based on what we discussed before, it is a bit better, but the magnetic field lines are still a bit too short. Can we actually fix that? Find any relevant bits in the code and try and fix the lines?
Extending magnetic field lines. I'll make the field lines even longer and more visible by adjusting several key parameters in the field line generation code. The main issues are field lines.
Okay, you can do it quietly. Not sure why it's reading the code. It's actually is better when I increase the strength. It looks more legit. Is it? Not sure. Yeah, we have the force. The yellow ones are force lines. So that's kind of nice. Yeah, we can make a total chaos out of it by adding another full-on chaos with 4 magnets on the screen. That was the bot, the agent. It restarted the thing for us. Restarted the thing. Okay, this is actually better. What we had originally. Okay, this is much better. That's a keeper. Claude 3.7. Thank you very much. Thank you very much. Hey, can we also check if there is anything wrong with the sliders? They seem to be discrete instead of continuous. Is it intentional? Like I'm able to click on them, but I'm not able to just move my mouse cursor while pressing the slider. Is this intentional?
I'll analyze the issue with the sliders in the magnetic simulation and provide a solution. Problem analysis, slider functionality. The sliders for magnet strength and orientation are indeed behaving in a discrete rather than continuous manner. The issue is that the event handlers are only set up for the input event, but there's no specific handling for mouse drag operations on the sliders.
Okay, that should be an easy fix, isn't it? Should be an easy fix. Thank you very much. And by the way, magnets are surely related to biomedical engineering and data science, so can explain that. We'll actually have to add it to... Yeah, I wish the agent was a bit quicker. Well, I guess we can use a different model. We can use a quicker model. Currently it's Claude Sonnet 3.7. Okay, now we have this, yeah, a lot of strength to the magnets. I don't see where's the lines? No, I do see the lines. You can flip. Yeah, it looks pretty good to me. I don't know, are there any magnet experts watching this? Layout works on all screen sizes without overflowing. Oh, right. And for showcasing, yeah, we want, well, that's for educational purposes. Like when you load the page and you don't know what is it you're looking at, we'll have a play demo button that automatically cycles through all the predefined functions. So we have Claude Sonnet 4. Give it the whole code into a single page interactive simulation animation game. Claude Sonnet 4. Do we trust Claude Sonnet 4? Well, even if it's not relevant to biomedical engineering / biomedical data science, at least we are learning how to use those these code generating models. Doesn't make sense calling them language models. They're more like, well, currently we're using JavaScript, so what are they? JavaScript? What? It's still discrete? Yeah, the buttons are still discrete. Didn't we just change it before? I thought we did. Yeah, 4 magnet chaos. What's the strength like? Should we just pop all the strength up to max? Yeah, now they're going. Yes. Oh, it's just gonna all get stuck, laid up on top of one another. Poof, poof. Yeah, chaos, magnet chaos. What's going on? Maximum 4. What? I didn't program for that. Yeah, seem to cancel each other out. Okay, Claude 4 is really not lazy. Keeps going, editing the code. Oh, okay. Change things, didn't we? Okay, the mouse still works. The fields look legit. We have an equation. Force between magnetic poles. Simplify. Okay. We have a demo. Add magnet. Add magnet. Add magnet. Only 4. I can only do 4. That's okay. Strength. Not the... Yeah, the... I can't scroll those... flip. In the section below the canvas where we have the text, can we add a whole section, a text paragraph about how magnets are relevant to biomedical engineering and data science? So obviously the obvious aspect is how they are used in imaging, but potentially other applications as well. We tried changing it before, but I think it didn't quite work. So with the scrollers, currently they are discrete. I cannot click on the scroller and just change the parameters. So this is both for strength scroller and angle scroller. Can we fix that somehow, or would it be too hard?
I'll fix the slider interaction issue where you can't directly click on a specific point of the slider to change the value. This is a common UX problem where input range elements only respond to dragging, not clicking at specific positions.
Wait, I think it's actually the other way around. Can you explain first and then change the code, update the code accordingly? It's the other way around. I'm able to click on it but not slide.
Currently, the sliders in the magnet controls have the opposite problem from what you initially described. You can click directly on the slider track to set...
Okay, can do it quietly because I don't like this this robotic voice. We don't want to hear that. Yeah, once you hear something like NotebookLM, you can't go back. Sorry. Any other robot voice model? Respond direct clicks. Okay, the mouse is working. Okay, Claude Sonnet 3.7. Thank you very much. It's working really nice. Okay, we have 10 minutes of NotebookLM. So if you don't like AI, this is your time to stop listening or watching, because the robots are coming. The robots are coming. So I'll do a 10-minute review of everything we've done of this web application, brought to you by Google's NotebookLM.
Welcome back, everyone, to another deep dive. Today, we're jumping into something really fundamental, kind of invisible, actually, magnetism. And we're using this amazing interactive tool to help us get a handle on it, the magnetic playground simulation.
Yeah, so our plan today is, well, first, just touch on the basics. What is magnetism? Then we'll really get into how this simulation, this magnetic playground, makes these complex physics ideas feel, real. Almost playful.
Yeah.
And then this is the really cool part. We'll see how it all connects to like biomedical engineering, data science, surprising stuff. Okay, let's unpack this.
Absolutely. And what's fascinating here is that understanding these invisible forces, it isn't just academic, right? It's really the foundation for so much of our modern tech. It's amazing how a, relatively simple simulation can shed light on principles behind things like MRIs or even data storage.
Exactly. So maybe let's start right there. What is magnetism fundamentally? I mean, we know it's one of those basic forces in nature. It comes from moving electric charges. And every magnet, it has the two poles, north and south.
That's right. And they create these invisible magnetic field lines stretching out into space.
Precisely. And those field lines aren't just conceptual. They represent a real force field. We even have a simplified formula for the force between two magnetic poles. F equals K times M divided by R squared. Basically, it tells you the force depends on the strength of the poles, the meh and ms, and crucially, it decreases really fast with distance, RCI. That's the inverse square law. Double the distance, quarter the force.
The inverse square law, that pops up everywhere in physics.
It really does. And another key point here is that magnetic fields are conservative, which essentially means energy isn't lost or gained overall in the system. It just changes form, like between potential and kinetic energy.
Okay, so we've got the inverse square law, energy conservation, and the really basic rules that I think most people remember. Opposite poles attract.
North pole, south.
And like the poles repel.
North pushes north, south pushes south.
Yeah, simple rules, but they govern some pretty powerful interactions, don't they?
Absolutely, and that's where seeing it helps.
Right. Talking about invisible forces is one thing, but how do we really, get a feel for them? And this is where the magnetic playground simulation comes in. It's designed specifically to let you explore these forces, see them happening. It uses, real-time physics and field line visualization. So you actually watch the magnets move realistically. Here's where it gets really interesting.
It really is. The hands-on part is key. The source material explains how you use it. You just use your mouse or even touch. Drag the middle of a magnet to move it around the screen. Or if you drag near the edges, near the poles, you can rotate it.
Oh, neat. So you can position and orient them exactly how you want.
Exactly. And there are sliders, too, so you can adjust the strength of each magnet and its orientation precisely. Real-time updates. Plus keyboard controls for quick actions.
Like what?
Well, spacebar adds a new magnet. R resets the whole thing, clears the board. F is really useful. It toggles the field lines on and off so you can see them or hide them.
Ah, okay.
D starts and stops at demo mode, which is kind of cool to watch. And A toggles the audio if there are sound effects associated with the interaction.
And it shows the forces, too.
Yep, with force indicators, little yellow arrows on each magnet. They show you the direction and, implicitly, the strength of the net force acting on it.
Yeah.
It makes it all very, very tangible.
It's fantastic how a good interface makes complex physics so much more approachable. So this isn't just for playing around, though. It demonstrates specific physics concepts, right? You mentioned the field lines, visualizing direction and strength.
Exactly. And you see the inverse square law directly move a magnet away, watch those force arrows shrink. It also shows superposition really well when you have multiple magnets.
Ah, right. Things get complicated.
Yeah, their fields just add up. The simulation calculates that combined field instantly, showing you these intricate patterns that emerge. It's not just one magnet influencing another, it's the whole system interacting.
That's a key concept.
Definitely. And conservation of energy, too. You can push magnets together, give them potential energy, let go, and watch them fly apart, converting it to kinetic energy.
Yeah.
You might oscillate for a bit.
Until they settle down, maybe due to some simulated friction or damping.
Right. And finally, torque and rotation. You can see how off-center forces make the magnets twist and turn to align themselves.
So you learn these core concepts by doing, essentially.
Precisely. And that leads naturally into trying out little experiments, like you could try to achieve magnetic levitation. It's tricky. You need to balance the attractive and repulsive forces just right.
I can imagine. That would be a fun challenge.
Or just watching carefully how those field lines behave. See how they stretch between opposite poles but curve away from poles. It reinforces the rules.
Testing the strength slider too, I suppose. See how a stronger magnet reaches out further.
Absolutely.
Yeah.
How does doubling the strength change the interaction distance? You can measure that, roughly. Or just throw 3 or 4 magnets in and see what happens. You get these really complex, sometimes beautiful equilibrium patterns.
Exploring the complexity.
Yeah. And watching the energy transfer during oscillations is quite insightful, too. But, playing with this naturally makes you think. This raises an important question. How do these simple rules, these interactions we see in the simulation, actually apply in the real world, beyond the playground?
That's the perfect pivot, because it's easy to think of this as just, physics homework or a cool visualization. But these principles, the very things the simulation shows us, attraction, repulsion, fields, forces, they're absolutely foundational to some major modern technologies.
Yeah.
You mentioned biomedical engineering and data science. So what does this all mean? How does it connect?
Well, the connection is incredibly direct and impactful. Let's take biomedical first. The huge one is MRI magnetic resonance imaging. It uses incredibly powerful magnetic fields, far stronger than these little simulated magnets, along with radio waves. But the fundamental principle is manipulating magnetic properties, this time of atomic nuclei in your body, mostly hydrogen in water, to create unbelievably detailed images of your organs, tissues, brain, everything.
Without cutting you open, it's revolutionary.
It truly is. And it all stems from understanding and controlling magnetic fields. Beyond imaging, there's cutting-edge research using magnetic nanoparticles, tiny, tiny magnets.
Nanoparticles for what?
For things like targeted drug delivery. The idea is you attach drugs to these magnetic nanoparticles, inject them, and then use external magnetic fields to guide them precisely to, say, a tumor.
Wow, so you could deliver chemo right to the cancer cells and minimize side effects.
That's the goal. It's still largely experimental, but the potential is enormous, based on the same fundamental magnetic principles.
Okay, that's biomedical. What about data science? That seems like a bigger leap.
Maybe less obvious, but definitely connected. Think about those MRI machines again. They don't just produce pictures. They produce vast amounts of digital data representing the magnetic signals they detect.
Right, huge data set.
Exactly. And analyzing that data is a massive task for data science and machine learning. Algorithms are trained on thousands of MRI scans to automatically detect subtle anomalies, maybe early signs of disease that a human eye might miss.
So AI reading the scans.
In a way, yes, or assisting the radiologist. They can also be used to predict how a disease might progress, or even to improve the quality of the images themselves, maybe making scans faster or clearer.
So turning that complex magnetic field data
Into life-saving clinical insights. That's the essence of it. And interestingly, even this relatively simple magnetic playground simulation, it models complex system interactions, right? Multiple magnets influencing each other dynamically. That kind of system thinking is exactly what data scientists do, trying to understand and predict behavior in complex systems, whether it's magnetic fields or, customer behavior or climate patterns.
That's a really powerful connection. From a simple virtual magnet interaction to predicting disease from complex data. And the simulation itself isn't standing still, is it? The source mentioned potential future enhancements. Things like different magnet shapes, not just these simple dipoles, but maybe circles, horseshoes, bars.
Yeah, that would add another layer of realism.
And adding magnetic materials like simulated iron filings that would physically line up with the field lines.
Oh, that would be visually fantastic for understanding field shapes.
Or electromagnetic coils, showing how electric currents create magnetic fields.
Bringing electromagnetism fully into it, that's a big step.
Maybe 3D visualization, measurement tools like a virtual Gauss meter to read field strength.
Make him more quantitative.
Even historical examples, or including the Earth's magnetic field. Lots of possibilities.
It really shows the potential. And if we connect this to the bigger picture, it just highlights how these tools, these simulations and visualizations, are becoming so important for learning and discovery. By making complex physics intuitive and interactive, they accelerate our understanding. And that understanding fuels innovation across so many fields.
It really drives home the point, doesn't it? We went from these invisible forces, these simple north and south poles attracting and repelling in a simulation, all the way and understanding technologies like MRI that see inside the human body and data science techniques that help save lives. It's quite a journey, starting from visualizing the invisible with a tool like the magnetic playground.
It absolutely is. It makes you appreciate how fundamental these forces are and how powerful visualization can be for grasping complexity. Kind of makes you wonder what other invisible forces or complex interactions are shaping our world that we just haven't found the right way to see yet. Thinking about everything we've discussed, from the basic physics to the advanced applications. What stands out to YU as the most surprising connection or idea from this deep dive?
Yeah, that was NotebookLM. So we just did this simulation earlier and then turned it into this code. I really like the user interface and everything. We had the prototype made by Gemini 2.5 Pro, and then we finished with Claude, both Sonnet 4, 3.7 thinking, and just 3.7 to fine-tune the code, essentially make it ready for production, because everything we do is available on BioniChaos.com. Go check it out. Let us know what you think. This Fourier transform visualization. So don't forget that meant to be a like. and with 25 vectors. It's actually repeating the drawing we made. Yeah, again, 25. We'll be able to make it, or do we need more vectors? It's doing fine. Can slow it down, zoom onto where it's currently drawing. Yeah, you can see all the vectors. So there are 25 of these lines. They calculated essentially real time, which is pretty amazing. We're calculating all the vector length, and they're just rotating around one another. I can speed it up again. So yeah, like, subscribe, and tell your friends, and check if they are working. Yeah, seem to work very well. You have this keyboard shortcuts, adding more magnets, as the robot explained before. Can increase the strength of each magnet and see how they interact. You have all this description. We used to put this NotebookLM description on the page. Well, now they'll just be on YouTube. Hope you don't mind. And that's the other one. Yeah, it says this lazy loading. Yeah, eventually it's loading. Hopefully it's loading from the CDN. Can close this. You have shortcuts. You need to remember the shortcuts, keyboard shortcuts. 1, 2, 1 and 2. Yes, so 2 is toggling the vessel overlay for your convenience. And 1 is toggling the mask. The mask is just making it like very opaque, so that when you have the vessel overlay, you can actually see it better. But if you remove the mask, you can actually see the original image, and the overlay vessel overlay is semi-transparent. And this semi-transparent vessel overlay was actually drawn by hand. Amazing that someone actually did it. Thank you very much. You have this diabetic retinopathy, where you have this extra vascularization, I think it's called. So yeah, so they were labeled. It's a great data set where someone did the vessel overlay by hand. Quite amazing. There's not many images though, but yeah, still quite a skill, quite a task. So thank you very much. Yeah, that's where the original dataset is. Is that link? Yeah, website. Well, anyway, it's somewhere on that website. And yeah, so you can actually review the data, review this dataset. And we have this new magnetic simulation thing going on as well for you. Hey, go check it out. Let us know what you think. Don't forget to like, subscribe, unsubscribe. You know what to do.